turn on the recorder since that may be an important thing to do this evening. First off, let me apologize for the mix-up and sort of the scheduling thing. I know that I had originally said we wouldn't meet tonight and we'd meet next week, but as I kind of began to look at the schedule and look at the commitments that are out there, it occurred to me that we needed a couple of sessions kind of up front here. And so, there'll be some stuff within this session that will provide as a recording for other folks that is kind of essential to understand the basic structure of statistics and what it means to get into statistical analysis. I do have dates set, and I've put those up on the As You Learn page. If you go to the As You Learn page, you'll see, in the banner up there where it talks about the synchronous schedule. The dates are up there, and they are September 4th, 11th, and 25th, October 9th and 23rd, and November 6th, 13th, and 20th. And, I'm not saying that we will necessarily end up meeting all those dates. If we're not going to meet on a particular date, I'll give you a couple of weeks heads up. But you can be assured that we will not meet on the dates that are not on that list. So I've crossed off some dates that I know that I can't meet on. And it's a combination of, some I guess there are a couple of university holiday periods in there, and also some meetings that have to be at Boone early the next morning, or Raleigh one week, and so it's just kind of a crazy schedule. But this is kind of what we're stuck with, and it'll work fine because we'll do what we can do and what we need to do in synchronous sessions, and then most of the work will be done outside of synchronous sessions and sort of async sessions. And if there's a piece of content that I think would be enhanced by me delivering it or talking about it a little bit or something like that, we certainly will do a recording of that if it's not going to fit into the meeting schedule, and put up a recording of that up on YouTube and obviously link it to As You Learn. So, we'll work through this. I've been playing with these courses a little bit in terms of making sure that we don't meet any more than is useful for you to meet. And that seems to be a concern among students with online courses, that we don't meet sessions that are not terribly useful to you. And so we'll kind of go with the schedule, and hopefully it works out well. And as I said, if I determine that there's some date on there that we're not going to meet that's on the list of meeting dates, then I'll give you a good heads up. It might not be 2 weeks. It might be a week or 10 days or something like that, but I'll give you a heads up. We're not going to meet. Okay, any questions about that or any? The 6 o'clock is a time that, I just chose because it seems to work a little bit better in my schedule as opposed to a little bit earlier. And, if we can always tinker with that if we need to, but no one has expressed a concern there. So we'll just go with that. Okay. All right. This is going to be a little bit of a presentational night because there are 3 or 4 concepts I want to put out there that are absolutely essential to understanding statistical logic and statistical theory. And so I want to get through those as much as we can, and obviously we'll stop and answer any questions you have, or if you have concerns and you think we need to put something else up, I'll add to the resources or whatever to add a couple of things. I have plugged up a couple of new things on As You Learn just recently that I thought I might need for this session and kind of fill some gaps a little bit. And so if you haven't looked in the last half hour, you would have maybe not seen everything. But there are some basic concepts. And the second thing we'll do this evening is try to do a little bit of an introductory thing with JASP, just to give you a kind of a sense of what the software is like, what it can do, how to work with it. I mean, to me, it's very intuitive and very kind of user-friendly to use, to work with, and has all the information in it. So you're not going back and forth between different files and having to open different windows and things like that. It's all in kind of one program. And so we'll talk about some of those things and make sure that you have a sense of that. And then there will be an assignment that's up that I'll ask people to kind of attempt to work with between now and next week. And we may add a couple of little elements to it or something like that as we go through it. So that's the order of things. Question? Thoughts? Okay. There are not a whole lot of kind of bedrock elements to understand statistical logic. There's really only a couple, and then there's some sort of corollary elements to that. And so we're gonna talk about those things tonight, and it's the concept of randomness, the concept of normality, understanding error, measurement error, observational error, and then really just having a passing acquaintance with a couple of concepts of probability. And those things all kind of pull together or fit together to create the underlying framework around what statistical logic is based on. And all of those ideas, by the way, go back well beyond the middle of the 19th century, where we began to develop sort of the statistical logic. And so it wasn't as if these ideas were foreign or strange, or nobody really knew what they were and they were created out of whole cloth or something like that. These ideas existed. And, some of them go back as far as the Greeks, and some of them were, ideas that Descartes and some other folks came up with in the 16th century or early 17th century. And so, these ideas existed. They just didn't have really, beyond using them for their own purposes, they didn't really have a framework that pulled them together to create sort of this field of statistics, but they all work together. And the first underpinning under all statistical logic is the notion of randomness. The idea that when you're looking at subjects and you're looking at measurements about particular subjects, that there is you're looking at a random sampling of subjects. And so therefore their behavior is random. And there's not what we call a bias or any sort of anything that would impact whatever we might be measuring or whatever we happen to be looking at, because all their behaviors and all their things about them would be subject to just random variance and random fluctuation between individuals. I mean, if you put a bunch of individuals in a room and you look at them on any sort of measurement, height, weight, visual acuity, I don't know, whatever you might look at them on, there will be differences between people, but those differences, if there's no other structural influence at play, those differences will be purely random. And so people will be different because they're random. Well, as we know, people tend to be more alike than they are different. And that, we're probably, from one person to the next, we're probably 95 to 98% the same. And our differences are only, 2 or 3% at most. And so what distinguishes us as different is much, much smaller than what distinguishes us as like everybody else. And so randomness leads in certain directions. And one of those directions is in the direction of what we generally refer to as normality. And there's a little video. I don't know if you had a chance to look at this little video. We'll go ahead and play it here. It's only about 3 minutes, and hopefully it'll work okay. There's a little video that I found a few years back in which they are talking about what's called the central limits theorem, which is basically the way in which randomness generates normality. And so I'm going to see if I can pull that up. And where was that at? Okay, that's all right. All right. Now, where'd you go? I'm going to start this thing a couple of times. I'm going to start it, and I need you to tell me that, you're hearing the sound. Because for some reason, I may have to switch to a different monitor to generate the sound, and I don't know what the quirk is with this website, but it does seem to, have some issues with sound. And so hopefully you'll be able to, well, let me go find it again. Where'd it go? Let me go put it in frame. There we go. And then create a share. So if once I start this thing, if you will just let me know, either by shaking your head or whatever, waving, whatever, that you can't hear it, then I can we'll switch it around to a different thing. So hopefully this works, but let's see. Can you hear it? Okay.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average, and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group. So he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables, even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Buthikrit Bhattacharya. This video was created by Shui Cho and brought to you by CreatureCast. Special thanks to Casey Dunn. For more stories, visit creaturecast.org.
Okay. Let me make sure this thing is off. Okay. Oh, okay. So good. I was afraid I looked at the chat, you'd say, I can't hear it, and we've just finished it, but no. There are a couple of sort of key points there. One is that normal distributions or a normal distribution is not a mathematical artifact. It's a universal kind of law of nature that when you have multiple measurements of something, or when you have you look at a large distribution of something that's random, what you'll discover is that it will always have a distribution that looks what we call this traditional bell curve, this normal distribution. Now, if it's not random, okay, then you've got something else going. And what about the bimodal dragon wing thing? Well, obviously there was a structural difference because there were different, quote unquote, species of dragons. So there was another factor at play that was not random. And so that's why it was, they talked about the bimodal thing. But when you sample, when you do random sampling, sample means are always distributed in a normal pattern. And that's the basic strength of the modern scientific method, where statistical logic came from, is if you work with samples and the samples are random, sample means will always be distributed in a normal manner. Normal means predictable. And so therefore you can compare, say, the overall mean of the population. You can compare one sample to that population. Or you can compare two samples against each other, or three samples, or four samples, or however many. Because what's important is that because you are dealing with, once again, random behavior, then you have a predictable outcome. Now, there is a wrench in the works of that, a monkey wrench in the works of that, and that is that very seldom do we have purely random. It's hard to get purely random samples. From a practical, logistical sense, they're very expensive to do. And from a logistical sense, it's almost impossible to get them anyhow, because it's almost impossible to have access to a population that you're able to randomly assign people to some treatment versus some placebo. Now, we do that in medicine, and we call them double-blind studies. And there are studies in which you do randomly divide a sample or a population, or you randomly divide a group of people. It's not necessarily a random population. You divide them randomly into two groups. One group gets a placebo, one group gets the real treatment, the real medicine, and neither group knows what they're getting, and neither do the doctors that are giving it to them. That's why it's called double-blind. And so there can't be any bias passed along from a doctor's perception or a healthcare professional's perception that this person will be getting better or not or whatever. Yeah. That's one of the few cases in which you will actually see, like a purely random scenario. But almost in everything else, it's just hard to find random, because it's not like you can randomly grab a population of people and give half of them a certain disease and the other half not. I mean, you have to draw from a population that already has the disease. And so it makes it almost impossible to do purely random stuff, except in double-blind experiments. Now, let's look at a couple things about normality. A common normal distribution is what's called a standard normal distribution. And it's when a set of data, a set of numeric data, is transformed into what are called standard units, standard deviation units. And so you take a particular population that has a particular average on some measure, and you calculate what's called standard deviation. And that's really a measure of random error. And the normal distribution for a sample or a group measurement that's translated to normal scores or standard scores, z-scores, whatever you want to call them, using standard deviation, will be distributed almost perfectly this way. So that about 68% of the cases will be between one standard deviation above the mean and one standard deviation below the mean. About 95% of the cases will be distributed between two standard deviations above the mean and two standard deviations below the mean. And almost over 99% of the cases will be distributed within three standard deviations above and below the mean. Now, anything outside of that are considered to be outliers. Actually, anything outside of the middle 95% is considered to be a significant outlier. And so here's your first encounter of the term significant. In the social sciences, they call it the rules of two. And two means two standard deviation units away from the mean. And what that means is that if you lie within two standard deviation units, you're considered to be within the range of what differences could be accounted for by random error. If you're outside of 2 standard deviation units, then you're outside of the range of what we would call standard error, and so there must be something else going on. Now, we will come back to this, but I just wanted to introduce this now because we're going to go to a second concept, and it's the concept of error. So, any questions before we kind of jump off in a different direction? Okay, we're coming back to this a lot, so don't be too concerned about it. All right. So, well, wait a minute. I do want to do one more thing first. Something that may raise a question in your mind is that, okay, we're talking about things that are measurable. We're talking about a score on something. We're talking about, you know, some test that has a particular score available, or some medical measurement that has what we call a continuous variable attached to it, like, you know, weight or you know, blood pressure, or I guess cholesterol numbers or whatever, that those are on a what's called a continuous scale. But what about if you're talking about something that's not that way, something that's, say, you know, dichotomous, yes, no, or use the classic example, heads and tails. How can things like yes, no, and heads and tails be distributed normally? Well, I want to show you what that looks like. Give me just 1 second here. All right, let me bring this up. Now, this is from a handout that I put up, and we're going to use this several times during the course, and I'm going to use just one little piece of it today. And it's called Introduction to Probability and Statistics. It's a source off of the web that's typically pretty good. I think the citation is at the end. If not, I'll have to double check that and make sure that I put the citation on there. But you know, most of the things we do in the sciences does involve quantitative data, and therefore we are dealing with you know, quantitative scaling. And so that means it's in the realm of probabilities and in the realm of statistics. But let's say you flip a coin 4 times. If you flip a coin 4 times, if you take a coin, you flip it 4 times, you're going to have a number of different outcomes. As it turns out, you're going to have 16 unique outcomes. And in one of those ways, one of those unique outcomes, it's going to be no heads at all. In one of those unique outcomes, it's going to be 4 heads. In 4 of those unique outcomes, it's going to be 3 heads. In 4 of those unique outcomes, it's going to be 1 head. And in 6 of the unique outcomes, 6 of the 16, it's going to be 2 heads. And so if you flip a coin, you know, you could take this graphic and you flip a coin 16 times, basically 4 times, you're going to have 16 possible outcomes if you count up across the 4. Or if you flip 4 coins and look at how they're laid out, you're going to have 16 possible outcomes. You either flip 1 coin 4 times or 4 coins once. And so you have odds that, and we're not going to get into the odds and the probabilities at this point, but if you distribute those outcomes from 0 heads to 4 heads, and so you have 1, 4, 6, 4, 1, that distribution begins to take on the shape of normality. If you flip that coin 8 times, it becomes to look more normal. If you flip it 16 times, even more normal. 32 times, even more normal. And then finally, 64 times, even more normal. And I guess you could go to 128 and it's even more normal. Not only does it become more normal, it becomes skinnier. So that most of the cases lie right at the middle. So even when you're tracking dichotomous outcomes, heads or tails, over a number of different attempts or a number of different tries, it becomes more and more and more normally distributed in aggregate. When you look at you keep track of all the different tries, all the unique different tries, unique different outcomes that can exist. So normality not only exists when you're dealing with, say, a score or a measure that is quantitative like a score, but it also exists when you have what are called categorical outcomes. In this case, heads or tails. You could do the same thing with a die. 6 potential outcomes, 1 through 6. And you could roll it a number of times. And what you would find it would do is that the distribution of the outcomes would become to look normal. And so it's not a mathematical concept. It's a purely logical concept and an observable concept. It's observable in nature. And the more instances you look at, the more normal it becomes. Now, true normality can only exist when you have an infinite number of measures, infinite number of cases, infinite number of occurrences. And it happens for everything at that infinite number of cases. So it doesn't matter how you're measuring, whether it's categorical, heads or tails or whatever, or it's a particular score, eventually the distribution will become perfectly normal. And there is only one distribution of outcomes at infinity, and it's the normal distribution. And it's just a law of the universe, law of the cosmos. Now, we can quantify it, obviously, and we can make some sense out of what it means, but it still is just there because it's just there. It's observable and it's universal, normal distribution. Now, at the heart of it, though, is this idea of randomness, this notion of randomness. Now let me go talk a little bit about error, E-R-R-O-R, for those of you that have problems with my North Carolina, Virginia mountain border accent. Anytime we measure something in any way, there is what's called measurement error. It always exists. And it may be related to, the imperfection in how we measure things. It may be related to the imprecision in how we have defined things. It may be related to, people responding in a way that is inconsistent from time to time. I mean, there's all kinds of reasons why there's error that exists anytime we measure things. The only thing we can be sure of is that anytime we measure something and we have an observed value, there is a component to that observed value that is error. And so if we have a value of, say, X, we know there's a true score piece, the T, and we know there's an error piece. Yeah. As it turns out, there are actually two error pieces. There's an error that is random, just happens because it happens, differences between people, differences in precision, differences in whatever. It's purely random. There's no real quote unquote cause to it. Be careful of that term. Cause there is no real ever cause and effect, but let's say, it's random because it's random, because it's just, people just differ on something. And then there's what we call systematic error. And that's an error that's created because of some other element in the measurement environment that's not random. Maybe it's the gender of the respondents. Maybe it's the way in which they perceive the language. Maybe it's you've got two people, you're measuring one day and it's a bright sunny day, and you're measuring the other one the other day and next day and it's rainy and dismal. But there's a reason that systematic error exists, and it's not random. Its effects will differ from person to person. Now, that can be gender, can be any number of things. Could be whether you're in the treatment group versus the experimental group versus the control group. And so there's always that second type of error, that systematic error. Now, the problem is we can think about ways to measure random error, to quantify and measure random error, because when things are random, they're normally distributed. And so we can talk about, what's the margin of error, what's the spread of the random error, how likely is the score to be, over here versus over there. And so we can understand random error. We can't know or understand systemic error. And so that brings us to how do we go about doing that? How do we understand whether something is systemic or whether it's random? Well, that's the underlying concept in any sort of statistical artifact, whether we're talking about T scores or Z scores or F scores or R scores or whatever statistical score we're talking about. Every single one of those is structured in that there's a ratio, and on the top of that ratio is the observed value or the observed difference between two groups or whatever we have observed. And on the bottom of that ratio is an estimate of random error. And we generally call that estimate of random error an unbiased estimate of random error, or an unbiased estimate of error, because we want to distinguish that which is random from that which might not be. Yeah. Sometimes we call systemic error or systematic error bias. And it's always the bias that we're looking for, that we're trying to figure out whether a difference, say, between two groups is impacted by the systematic error that's created by the difference of being in a control group versus an experimental group, or the difference between being male or female, or the difference of being in a raised in poverty versus raised with affluence. And so we're always wanting to know whether that bias created by differences in subjects and differences between groups is having an impact on the overall observed outcomes. And so every statistic is a ratio of whatever the observed outcome is, whether it's individual scores or differences between groups or differences between multiple groups or differences between random probabilities and what we would expect to see and what we actually saw. And on the bottom of that ratio, on the bottom of that fraction, you don't like the word ratio, on the bottom of that fraction is an unbiased estimate of random error. Now, we also know that all those statistics, just like everything else in the universe, is normally distributed at infinity. And as we pull back away from infinity, the distribution may not look normal, but it's simply because we're looking at fewer cases than infinity. But ultimately, all statistics have the same distribution, but that only happens at infinity. And so as we pull back away, the distributions may look different, but they actually share the same logic and the same way of understanding whether we're looking at a difference or looking at a relationship that we would classify as significant. Significant meaning that there's a less than 5% chance, and that's just a standard we use, that there's a less than 5% chance that this is purely random. Now, there's a lot to take in there, and we'll cover a lot of that individually as we go through the statistics piece. We'll come back and kind of revisit all of that in lots of different ways. But that's essentially all the elements that there are to statistical logic. There is the random piece. The random piece leads us to normality. The normality piece, over lots of iterations of things or lots of different bits and pieces of data, leads us to a predictable distribution. And what we are distributing is a statistic, whatever it is, in whatever case, whatever statistic it is for whatever type of data we're looking at, that is the product of a comparison between observed outcomes and unbiased estimate of random error. And that's all the logic there is. Now, the cases vary. The cases vary, and the stats vary based upon. Let me stop right there and see if there's questions, or if you're not sure you have a question yet, you think you probably have a question, you just don't know what the question is. Any of that? You notice there's not a single formula there except for the little ratio thing. I didn't even give you a graphic that had that on, because I don't want you to think math. I want you to think logic. Hang on just 1 second. Okay. Now, I mentioned that understanding statistics and understanding what statistic is used is subject to the type of variable, the type of data that you're dealing with. In almost all cases, you have 2 bits of information. It might be 2 different measures. It might be one measure that defines the groups that people are in and some outcome variable. It might be, it may be pre-post measures, pre-post data. It could be all kinds of different data. But the actual variables themselves are basically fall within 2 definitions. The nature of the variable themselves fall within 2 definitions. And so let me throw that up there. Okay. There are technically 4 different kinds of measurement in terms of what the characteristics of the actual variable itself. There are what are called nominal bits of data. And that means that somebody is in one group or another, or in one of 3 groups, or one of 4 groups, or however many groups there are. Male, female. Couple of different dosage levels, and a placebo. That would be 3 groups. And so the very fact that you're in one group or another, one group as opposed to others, maybe is a better way to say it, makes it nominal. So you're just in group 1, 2, 3, or 4, or A and B, or whatever grouping you may define them as. Now, if those groups have a natural order to them, say freshman, sophomore, junior, senior, or income 0 to 20,000, 20,001 to 40,000, 40,001 to 60,000, there's a logical order to the groups. Then they can be what are called ordinal. Still means they're nominal, just means there's an additional characteristic they have that makes them ordinal. Nominal measures and ordinal measures are what we would consider to be categorical. They're categorical bits of data. If the data is expressed on a scale where each equal interval has the same value, say temperature, a degree is a degree. Doesn't mean it's any different because it's between 95 and 96 or whether it's between 108 and 109. the value of a degree stays the same. The interval is equal. And so an individual measure on it is part of an interval scale. Age, a year is a year. Doesn't matter where it occurs, between 3 and 4 or 103 and 104. A year is a year, no matter where it falls on the scale. And so an individual score would be somewhere on that interval scale. Now, if that interval scale has an absolute 0 or an absolute end, not many do. One that comes to mind is temperature. There is a point at which temperature ceases to exist, absolute 0. There is a point at which age ceases to exist. You're born. That's the point at which your age begins, at least in our traditional definition. And so if an interval scale has a unique endpoint and not an artificial endpoint, just an endpoint that actually exists in nature or in totality, then we call it a ratio scale. Well, interval scales or ratio scales, lump them together, it's called continuous variables. So we have two kinds of variables. We have categorical variables that can be either nominal or they can also be nominal and have ordinal value to them. Or we have continuous variables that can be interval or they can have the additional bit of data and be a ratio scale. But there are only two types of variables: categorical and continuous. And depending on the structure of the research question and which one of those variables is, say, the independent variable versus the dependent variable, think cause and effect, although I know we can't have cause and effect. Think cause and effect. If you think cause and effect, the cause variable is the independent variable, the effect variable is the dependent variable. So depending upon the nature of the data that defines the independent variable and dependent variable, and the nature of the research questions, there are a number of different statistics that have been created to answer all those different questions, fit around those two types of variables, two types of data. And so that's the way in which individual statistical processes developed, but it's also the way in which we determine which is the appropriate statistic to use in a particular setting is by the nature of the question and the nature of the independent and dependent variables. In the traditional modern scientific method, we have an experimental group and a control group that are categorical, and then we have an outcome variable that's interval. Doesn't have to be that way, but that's the way the modern scientific method was developed. And so that was one of the first sort of statistical pieces of logic that had to be developed, was how do you deal with that kind of data? And that'll be some of the first things we'll look at this week and next week, or primarily next week. Okay, so are you ready to begin running for cover quite yet? All right. Well, this is the only, time we'll do this sort of thing. From here on out, we'll be working with real questions, real data, and, kind of how do you get at that? But, these are the underlying pieces. And that's, I think if more people understood how limited the logic is underlying statistics, uh, it wouldn't have the, the rap that it has of being, this thing that's just so hard to understand and so hard to deal with, because it is a relatively simple set of logics that goes into statistical inquiry. I'm often reminded, and I tell this story every now and then, well, every time I teach a class like this, but back in the middle part of the 19th century, in which they started to develop this statistical logic, because once they developed the modern scientific method, the problem was to understand when was a difference a difference. I mean, when was it a random outcome versus something that had a bias or a systematic root to it. And so they had to work through kind of a little bit of the mathematics of statistical logic. And so if you went back into the 19th century in England, where a lot of this occurred, England and a couple other places in Europe and a little bit in the U.S., what you find it was a society in which inheritance always went to the oldest male in a family, and estates were kept together. And so it wasn't like, if there was a big estate or whatever and there were 5 kids, it wasn't like they split it up 5 ways. The estates were kept together, and there was a name for it, and I can't for the life of me remember it right now. But the estates were kept together, and the title went to the oldest male in the household, and all the other siblings kind of, were lived at the pleasure of the oldest male. And you can imagine some of the dynamics that played out in that. But in the middle of the 19th century, what was happening a lot is that you had these, sort of these fortunes that came from empire, and as the empire was breaking up, the fortunes were going away, and so there wasn't a lot of money once the oldest male got control of things. There wasn't a lot of money to spread around, or a lot of resources to spread around, and so it was an incumbent upon the younger siblings, to get out and get a job. Well, the younger females, one of their primary jobs is going to be trying to find somebody to marry them, somebody to support them. But not only was that going to be an issue to find a job, period, much less, someone to marry them, they had about a 3rd to 5th grade education, because in England at the time, young females got about that much education, 3rd to 5th grade. And males got, maybe 8th grade to perhaps, a little bit of high school. And so the males were a bit more educated than the females. Well, one of the jobs that the females could do was go to work in a university or actuarial house, basically an insurance agency, insurance company, or a bank, and sit in the back and do the math. You keep track of the accounts, add things up, do all that sort of stuff. You kind of do the simplified bookkeeping that needed to be done in the background. Just doing all the math. Well, at the universities and some actuarial houses where statistics was being developed, rooms full of these young 3rd to 5th grade educated females would be sitting at desk doing the math, longhand, pencil and paper, and they had a title, and they were called calculators, because that's what they did. They calculated. And so all the underlying math in the development of statistics, which happened in the middle of the 19th century, was basically the underlying math piece was being done by rooms full of these young women with 3rd to 5th grade math skills. And so there's no high order math in statistics. The highest order math in statistics is to how to find a square root. And most times that's done by trial and error. Now, as mechanical counting machines came to be, adding machines, these rooms full of calculators went away. And not only did they lose their jobs by the early 20th century, but they also lost their titles. Mechanical counting machine was an awfully long title for the device, and so they simply renamed them calculators. But the title actually came from the now defunct title of these young women sitting in a room doing this math. So it's 3rd to 5th grade math at the highest. And so the thought process that stats is higher level math is, don't even go there. It's not. It's just 3rd, 5th grade math. Yeah, see, got a little history in there. It's not only a stats course. It's every now and just a touch of history. We'll throw a little history in. Okay. Well, let's take a quick break. I need to cut off the video because YouTube won't let me upload more than about an hour's worth in any one video. And need to take a quick break, maybe say 7:15, be back at 7:15. And we'll do a little quick introduction of JASP. Since we don't have a house full, we'll try to get a house full next week and see if we can do a little more detailed introduction next week. But we'll do a little bit, and that way you'll have a head start on it. And so let me turn this recording off.